In this lesson, we shall focus on MAT2615, tangent planes, calculus in higher dimensions, the chain rule, and other concepts that relate to calculus in higher dimensions. We begin our discussion by looking at the following. Right, as I indicated that we shall be doing literature review. There are certain things you already know, but we'll emphasize their significance because they are examinable. They appear in the exam most of the time, and also they appear in the assignments as well. And so there are those concepts that are very important, and we need to devote time to discuss. The chain rule is one of those results. All right, we agree that the chain rule has several versions, but we shall look at the kind of versions that are examined. For example, right, compositions of differentiable functions are also differentiable, powerful result. So in other words, if you combine through what we call the composition of differentiable functions, the resultant functions are also differentiable. Derivatives of compositions of differentiable functions can be defined, or rather be determined, by using one of many forms of the chain rule. All right, this is section 5.1 where the chain rule is stated for the composition of two R to R functions in also this section 6.2. Right, it is stated that the chain rule for the composition of an R to Rm function within R to R function. Right, so we now state the chain rule for the composition of an Rn to R function. So this is very important. Rn to R function within R to Rn function. Right, this is a generalization of a theorem, which is theorem 5.1.3. Well, I mean, you don't need to memorize, obviously, the theorems for this module quite. Right, with the gradient of f in the place of the ordinary derivative and the dot product in the place of the ordinary product. Now, the chain rule is very important. The theorem 7.6.1, let R bar be an R to Rm function and f be an Rm to R function. So we're dealing with two functions where R, it's a map, it's a function from R to Rn, and f, it's an Rn to R function. So in other words, f sort of does the opposite, and it runs from the codomain to the domain of the function R. If R is differentiable at t and f is differentiable at the vector function R of t, then the composition of the two functions f and R is differentiable at t, and the composition of f and R is the gradient of f dot, which is the gradient of f of R of t dot R primed of t. All right, so we have exactly that. Okay, why are we even doing this result? We're just stating this result because of the theorem 7.6.1. Why is it important, this? It is important because in the exam, you'll be asked many times to state the chain rule, and this is how you need to state it. Okay, the study guide has several versions of the chain rule, like different forms of the chain rule, but it's very important to note that if you're asked to state the chain rule, you need to say, let R be an R to Rn function and f be an Rn to R function if R is differentiable at t and f is differentiable at R of t. Then the composition of the two functions, f and R, is differentiable at t, and also the composite function of f and R primed at t equals the gradient of f of R of t dot R primed of t. Right, so this is the version of the chain rule that must be stated in the exam, and this is the version of the chain rule, I must state, that is expected to be applied in the exam to questions. If they say use the chain rule, they mean this, and that is why we're stating this. Okay, but it is very important to realize that, the chain rule has different forms. There's something we call the alternative form of the chain rule. Right. So now we are looking at what we call the alternative form of the chain rule. Let's look at these here. Right. So in other words, now we are looking at the fact that the chain rule itself has an alternative form. If we then suppose f is actually a differentiable R2 to R function of x and y differentiable, are both differentiable functions of t. Okay, I'm just stating the chain rule, which is another version of the chain rule, this particular version here. And this particular version obviously can be discussed here, or has been discussed. Then f can be regarded as a function of t alone. Okay, I'm just mentioning this one because it's also important, but also it is one version that normally does not often appear in the exams, but it is important in multivariable calculus to understand that if you actually are dealing with um, um, f as a function, f can be regarded as a function of t alone. And if f is regarded as a function of t alone, then it is possible to then be in a position to write the actual chain rule in this form. Now, if you understand that f is a differentiable R2 to R function of x and y, the function of x and y, so you'd have df dx, dx dt plus df dy, dy dt. To see this, put the r of t to the x at t, y of t. Then r is a differentiable R to R2 function, and df dt equals d dt of f of x of t and y of t, d dt, f of r of t. Okay, therefore this becomes the composite function of these. So in other words, this shows the actual relationship between these versions of the chain rule, because now you then say df dt can be written as the composition of f and r primed of t. But now it is actually this, which is the theorem by theorem 7.6.1. Okay, now where is theorem 7.6.1? It's exactly this one here, which states therefore that if you find the derivative of a composition of two functions, then it is the gradient of f of r of t times the dot r primed of t. And then now it becomes exactly this result, which is the df dx, df dy, dot dx dt, dy dt. Right, now taking the dot, it is the f dx, and obviously it's component-wise multiplication, so that you have df dx. And we note why this dot is important, because the gradient of the f function is therefore df dx, and we shall discuss this, df dx, df dy. But now the r primed of t itself is actually obviously an R2 function, and therefore you actually do component-wise differentiation, and now it becomes dx dt, dy dt. Taking the dot, component-wise multiplication, df dx, dx dt, plus df dy, dy dt. This can be extended for n variables in the obvious manner. Thus, we have the following alternative form of theorem 7.6.1, and we proceed as follows. Okay, obviously, this can be stated in a very compact manner. Okay, I'm just stating that because we shall use it just once today. And we have that if f is a differentiable Rn to R function of x1 up to xn, and xi is a differentiable R to R function of t for I equals 1 to n, then the f dt is the summation of the following. It is the summation of df dt, which is the summation of from 1 to n of df dxi, dxi dt. Okay, so something that you actually obviously are able to take note of there. So we continue. Right, we continue. So now, this is the, so this is sort of the version we stated last time, previously. This version here, which is the f dx, the x dt plus the f dy, dy dt, is the sum, and this sum is the sum of the products of df dx, the x dt. Okay, so, and we can see the df dx dt. The df dx is partial. So now you have that this one is the bent d, and these are the straight d's. And why is the d bent? This one is the partial derivative because we're dealing with f, a function of initially dxi, and now the xi's therefore are several variables. If you had to say f is a differentiable function of the x1 to xn, so we're dealing with f, a function of several variables. If you differentiate the function of several variables, multiple variables, you use the bent d to mean the partial derivative. Okay, but we're gonna just obviously show some examples. Let us look at these particular examples, like this example 7.6.1. I want us to discuss tangent planes and other things, but we need to prepare a little bit with some of these results here. Right, so at this point, if you're to look at how exactly, therefore, we need to be in a position to determine the answer to this in the exam. Okay, right. So, or in the assignments, but mostly in the exam. Consider an R2 to R function f and R to R2 function R given by f of x and y, which equals y e to the power x, and R of t equals cosine t sine t. You need to determine the composition of f and r primed by means of the chain rule. So let us determine these together by means of the chain rule. And therefore, if this is the case, we are looking at what actually we need to do in an attempt to solve this kind of a problem. Right, we need to obviously state up front the actual version of the chain rule that is required. But most importantly, we need to recall that if you have the composite function, so the composition of f and r primed of t, it is exactly the same as the gradient, right? The gradient of f r of t, like this, dot r prime of t, like this, right? And this here is the theorem that is stated here in 7.6.1, right? That the actual gradient of f and r, the composition of f and r, it's the gradient of f of r of t dot r prime of t. Okay, now we are just taking a look at this, and therefore what do we need to do first? Right, to be able to do this particular question, we take note of the fact that we must be able to first compute this here, and we must be able to compute that. So we must be able to compute the gradient. Right, so first and foremost, what do we do first? We find the gradient of the function f. So the gradient of the function f is the same as what? The gradient of the function f is the same as d1f, d2f, which is the derivative of this one with respect to x, which becomes y e to the x, the derivative of this one with respect to y, which equals e to the power x, like this. Okay, we're good, because the derivative, the partial derivative of the y is 1. Right, and we have exactly this. Now, what then do we know precisely? We have been told in this question that r of t is actually equal to the cosine there. And what does this mean? Well, it means, therefore, this gives us x and the y, right? And if it gives us x and the y, we take note of the fact that we have the r of t, which equals cosine t, the sine of t, which is r primed of t, which is the derivative of the cosine is minus sine t. The derivative of the sine is cosine t, like this. Now, what is this? And how do we obviously therefore consider this? We note therefore that this is x of t and this is y of t, and that is what r is. Right, and with that in mind, we're able to perform the following substitution. Right, and what is the substitution? The substitution is exactly what we have here. So if we have the gradient of f of x and y, right, so we have the gradient of f of x and y, which is y e to the power x. And then we have e to the power x. Okay, so in the end, then we have the actual substitution that is required. So this means that we can be able to obtain out of this here the required gradient, which means the gradient of f out of t, which is the gradient of f, the first component. So it's f of r of t. R of t is this one, which actually equals to cosine t sine t. Okay, but we are preparing for the tangent planes and other things. Right, so now, what then are we able to do out of this? Okay, we know very well that whenever we have the gradient, then the gradient is already this, of the x and the y. What is this? It is now you have the x. You have the y first. What is the y? Sine t. E to the power x, which is cosine t. X is cosine t. And with e to the power x, x is cosine t. It's cosine t, and therefore, this is what we have. We have the gradient. Right, we have the gradient. The gradient of f. Right, now with this in mind, we are in business and we're able to use the chain rule that is actually required, because now we've already got the things we need. We need to recall that for the chain rule, as stated, we need to take note of the fact that the chain rule itself, the composition of this primed of t, is by definition of the chain rule the gradient of f r of t dot r primed of t. So that in the end, then we have the composition here, which is r primed of t, which equals the gradient of this. And therefore the gradient is the same as what precisely? Right, we note that this gradient is this, which is the sine of t times e to the cosine t, which is actually the sine of t times e to the cosine t. And then we actually deal with the e cosine t as well. E cosine t, we dot. This is r, and then we find its derivative. We found the derivative, but derivative of the cosine is minus the sine of t. The derivative of the sine is cosine t. Okay, so we have the composition of these two functions. Right, using the dot product, we multiply component wise, meaning that we have minus sine squared t e cosine t plus cosine t e to the power cosine t, like so. Right, so, and this becomes the answer. This becomes the answer to that. Becomes the result. It becomes the result. It becomes the result. So we have exactly that. So, and obviously then we've used the chain rule to compute this particular derivative, which is at the composition of f and r primed of t. Next question. Next point. Right, in the next point, we try the next question. So now at this point, normally in the exam, they ask questions of this nature. Let us practice together at this point. And now, first things first, is to find we need to determine, because we've been given f of x and y, which is x squared plus y squared, and r of t equals 1 minus 1 over t and 1 plus 1 over t. We therefore need to determine the composition of f and r primed of 1. Now, we need to first get the gradient. Right, so first we find the gradient of the function f. Right, so if we find the gradient of the function f of x and y, now it is like d1 f, d2 f, which means is the derivative of these with respect to x, 2x, the derivative of these with respect to y, 2y, and would have the r primed of t. Right, the derivative of 1 is 0, the derivative of the minus 1 over t is the same as the derivative of minus t to the minus 1. T to the minus 1, the derivative becomes 1 over t squared. So that becomes 1 over t squared. This one, if you write it as t to the power minus 1, it becomes minus t to the minus 2 minus 1 over t squared, like this. Okay. Now, what then are we able to achieve out of this? Okay, the gradient. Okay, we have f r of 1. R of 1. Which is equal to the gradient of f. Now remember that we need to be able to compute this at 1. So we'd compute therefore the gradient of f at r at 1. Now r at 1 would actually therefore be the same as the following. So if you replace t by 1 in the r function, here it's going to be 1 minus 1, giving us a 0. And t is 1 here, which is 1 over 1. So 1 plus 1, 2. And we have that. What is then the gradient of this here? Okay, the gradient of f of this is 2x, which is 2 pi 0, 0, 2 pi 2 to 4. Right, and r primed of 1, which is the same as what? Right, so r primed of 1, we actually have got r primed here. And therefore, at 1, we will have 1 and minus 1, like this. Right, moreover, we then are able to observe that by the chain rule, we'd have the composition of this at 1, which is the grade of f by the chain rule. So if you value it at 1, it's going to be f at r at 1, r primed at 1. And therefore, the gradient of this therefore be given by the following.
Sir,
Yes, please.
why is it gradient f? I mean, yeah, 0,2. Like, how did we
Yeah,
get the 0?
yeah. Okay, that's a good question. That's a good point because we have added one. We have added one inside the function f. So if we have added one, need to remember what added one is. What is added one? Right, added one is this. Added t first, right, which is 1 minus that, 1 over t. So we've added 1, which is 1 minus that, and 1 over that. So this is exactly added 1. The 1 over 1, it's a 1. 1 minus 1, it's 0. This is like 1 over 1, which is 1, but 1 plus 1 is 2. So in other words, the added 1 is actually 0 and 2. Okay, right. And with that mentioned, it means that whenever we have the gradient of f at added 1, it's actually therefore 0 and 2 because we have added 1 is 0 and 2, but also we know that the gradient of the f function is double x, double y. So it doubles the 0 and you get 0, it doubles the 2, you get a 4. And this means that here we would have 0 and 4. Dot, they are primed, which is actually 1 minus 1. This and that would be 0, and this and that would be minus 4, and this is actually minus 4. And this is the answer. Which means we have R primed here, which is minus 4, like this. Minus 4, like that. Okay, so we have solved this problem using the chain rule. We have gathered every single bit of thing. And we have actually put the results together. We're just mentioning this because this is always there in the exam, but all the time. So it's one of those results you need to do this way. And most of the time, the question is going to be like, determine the composition of f and r primed at a number. So at this point, it's at 1. So it can be at any number. But now what is very important is following these steps because the marking memo memorandum would follows this pattern as well. Okay, now, however, I mean, this is how normally it comes in the exam, but we actually can look at other. Remember, this discussion is recorded, so even if you not copy the things, you would have access to this recording at the end of our discussion. But now, this function f is a function of 3 variables x, y, and z. So if you let f to be a function of 3 variables x, y, and z, which is x, y, z, where x, y, and z are functions of t, namely x of t is t cubed, y of t is t squared, z of t is t, use the chain rule to determine the derivative of df dt. Okay, so yeah. Use the chain rule to determine the derivative of df dt. Okay, we're just setting this one because this one is very important to know in calculus. We're dealing with multivariable functions, but I know in this module is not very popular in the exams, this particular result here. But now at this point, we need to be in a position to find the derivatives. But first we must find dx dt, because x is t cubed, then dx dt is 3t squared. We find dy dt, which equals 2t squared. Right, and okay, if this one is just 2t, okay, because if you have t squared with respect to t, it's 2t. dz dt 1 by the chain rule. By the chain rule. By the chain rule. Which means we have df dt. Which means we have df dt df dx, dx dt, df dy, dy dt, df dz, dz dt. So that you have df dt. Right, remember, use the chain rule to determine that. So look, we're looking at the chain rule as something that now spreads into like multiple terms. Why? Because we understand that f is a function of three variables x, y, and z. So that is why if you find a derivative of df dt, it says that now all the functions x, y, and z depend on t entirely. So that now we have df dt, right? But we know that f itself depends on x, y, and z, so that you need to have, say, df dx, which is the x dt, df dy is dy dt, df dz is dz dt. What is df dx? Right, so you find first df dx, and we look at what that is precisely. Right, so you need to take that actually exactly into account. What would the derivative of f with respect to x be? So we need to find that. We need to find that. Because f is x, y, z. What is df dx? Right, with respect to x, it's just going to become y, z. Right, it's just going to become yz. Now, if it just becomes simply yz, what is y? Right, y is t squared. Z is what? Is t, so that we have t cubed. df dy. Right, so df dy, final derivative with respect to y of this is going to become xz, because the derivative of the y is 1. Right, what is x? X is t cubed. Z is t. T to the fourth power. T to the fourth power. Okay, now there are a couple of things to do. Like if we need to find also df dz, okay, df dz is going to be xy only. What is x? T cubed. The y is t squared, t to the fifth power. Okay, so what is df dx? Right, so we saw that df dx is only t cubed. It's only t cubed. Right, and we have also seen the fact that we have also the following. If you have dx dt, what is dx dt? It's actually 3t squared. And then you have df dy. Df dy is t to the fourth power. dy dt is 2t. df dz is t to the fifth power. dz dt is 1. Okay, so this is like 3t to the fifth power, 2t to the fifth power, t to the fifth power, and this is actually 5, then 6t to the fifth power. Right. So we continue. Right, we continue
Yes.
as follows. Right, so we actually take note of the fact that we have found the answer. We have used the chain rule to determine the derivative of df dt. What is the answer? It's 6t to the fifth power. We move on to the next point. Okay, I know this is not difficult, it's very easy. Right, but there are other parts that we are building towards. Right, as part of a couple of activities that you need to do, determine as homework, right, you need to, during your own leisure, make the following, right, you need to try the following questions and say, for example, right, determine the following. The composite function of f and r primed of t by means of the chain rule in each of the following cases, which means r of t is 1 minus 1 over t, 1 plus 1 over t. And f of x and y is x squared plus y squared. R of t is t squared to t, and we have that. And we have that. All right. So now, so we need to obviously use exactly the same method like used before to be in a position to determine the actual result. Right. So right. So this one will serve as only a home activity. Right. Home activity. Right. So now this home activity is what you need to try on the chain rule. We have shown some examples on this, and we proceed to elaborate and use this in other cases. So now we then proceed to try the following here. The next thing. Right, so we actually have to practice. Now, number 3 is a function of 3 variables, and f is a function of x, y, and z, and is given as the sum of the terms there. But now I want us to be in a position to solve this particular problem in 1 point or in number 3. So if you need to determine the composite function, the derivative of the composite function of f and r primed at pi over 2, if this is the case, we need to remember a couple of things. So, but first things first, we need to take note of the fact that we're practicing so that you can be able to do this in the exam as it must be done. Right, we note that the function f is a function of 3 variables, x, y, and z, which is x, y, y, z, zx. And then we're able to find the gradient of x, y, and z. Right, we will first find the derivative with respect to x of this. What's the derivative with respect to x? This one, with respect to x, is going to just be y. With respect to x, is going to be 0. With respect to x, is going to be z. Right, so we continue. Right. The derivative with respect to y, this term, whose derivative with respect to y gives only x, with respect to y gives z, and with respect to y gives 0. The derivative with respect to z is 0. With respect to z, it's a y. With respect to z, it's x, like this. Right, so I'm giving you some good 2 minutes in your scribbler. Try to finish this particular question. The answer is going to be a number, and you share that number. So if the number is 1 billion, you will say 1 billion. If it's a trillion, you will say the answer is a trillion. But I'm giving you like some good 2 minutes to try this question. As soon as you're done, you alert me and say, okay, I'm done, then we shall do it together. I just need to keep your mind a little bit active. I know your mind is active, but yeah, it is important that I give you a chance to practice, because you can't just sit there idle, because then it's not good for your minds. Your mind must be active and need to engage. You need to engage in some activity. So we continue. We continue.
Yes.
Right, have you tried it?
I'm still
Right.
busy.
Oh, okay, that's fine. Thank you so much. Right, thanks so much, Naledi. Right. You let me know when you're done. I mean, we shall do it together. Just a question of practice, a little bit, yeah. I know we moved the screens. We're on a different slide now, but I wanted, yeah, there's no hard and fast rule. It's not a question of that fact that you expected to get 100% here. No, it's just practicing. Right. So you continue. Right. Okay, please. Let us when you're done, lady, and say, okay, now you're done. Let us when you're done. Please let us when you're done, when you're done, when you're done. Right. So, right, we're just keeping the mind active. We're just keeping the mind active because the mind cannot just, you know, stay idle. So it's very important for the mind to work. It's very important for the mind to work. It's very important for the mind to work. We're not in a marathon. We're just making sure that at least we're mastering the chain rule, and then we shall go to the tangent planes, and then we shall go to the potential functions. Okay, we shall spend time on potential functions also today. So yeah, something that it's important. But yeah, let's see how well you can do here. Let us see how well you can do here. Right, let's see how well you can manage this. Right. Okay. Right, so you continue.
I'm still busy.
All right, let's find things. Please alert me as soon as you're done, so that you can mark. Okay, so that you can mark. Remember, we're practicing. It's not a lot of questions on the chain rule. The others, you're going to do them during your own leisure. I'm just giving one. So that at least you can see what the answer is. Obviously, we did one where it was evaluated one, but now, even if it is, yeah, evaluated pi over 2 radians, we'll be able to understand exactly every single bit of thing. Right, so we're good. Once again, we're not doing so many. Sometimes I wish you can do, see those two, this one's in number 2. I wanted us to do, my initial plan was us to do all these during our discussion, but I know, if we just do 2, 3, it's fine. Then the others, you know, you can do, and then during your own leisure. But we need to just show the pattern. But we need more practice of the whole set of topics that must be known for the exam. Okay, and we need to like a lot of practice. So I have to spend time practicing. Like we do some examples, some we give to you, and then you share the answer. Because at this point, I'm just interested in the answer, and then we shall do it together. Because I've not done the question myself before, but I know that, you know, I mean, the math principles hold true. So we're good. Right. We continue. We continue. Right. I'm just interested in the answer. Just interested in the answer. And
Ngicela ungidownloadele ama-question paper awu-2 ahamba nama-memo wakhona. Ngiyacela nje, ngiyacela ukusiza.
all right. We continue.
Yes.
You're done, right?
I kind of done.
Okay, kind of. All right, that's fine.
Yeah.
All right. We're just practicing once again. Just I want to see what you're gonna do.
Yeah.
Because you're gonna be bored. That's my fear. Okay, if I just do this, okay, you have seen it, and then you see another example, another one. Okay, we did the examples
Also,
we've
I
done.
wanted to ask
Yes.
that my t value is theta over 2. It's not theta, but pi over 2.
Yes. Well done.
Okay.
So the value of t in this question is pi over 2. Is pi over 2 radians. Okay, it's just pi over 2. Yeah, but you see, every number is measured in radians, provided it's in degrees. Right, so obviously we know that our t is actually pi over 2. It's actually pi over 2. Right. So we continue.
Yes, you're not sure about my answer though.
Okay, it's long because it's a bit long. It's a bit lengthy. Okay, that's fine. Right,
Yeah.
because it's a bit lengthy, it's okay. Once again, I mean, the aim is not to get 100% here. The aim is to get 100% in the exam, but the aim here is to build the skill. And we always do it we always do two things at the same time when we're dealing with this. So what do we do here? We first do the gradient of this, and we also write the R of t. And this R of t, we just copy this one because the R of t is sine squared t cosine squared t with t, right? And then, so now what is the next step? The next step is to find the derivative of this. Okay, now the derivative of the sine squared. It's like the derivative of x squared. Derivative of x squared, you break down the 2, and then it becomes the sine of t cosine t. And then it becomes 2 cosine t minus sine t, 1. Right, so we have this. So that in the end, we're able to get the result. Okay, yeah, let's just continue because I just want to determine the answer with you now. I know very well that you tried a little bit. And the aim is obviously to try. Then what is the next thing? Like we did before, what we then do next is to compute what we got and what exactly do we compute. So we need to compute and then say we're able to find the following. Right, so we're able to say hence. Right, hence now we can be able to find the gradient of f r of pi over 2. Right, so, and this is the gradient of f. So, like, now, whenever t is pi over 2, so we then are able to substitute there. If t is pi over 2, then we substitute in the r function. Okay, we're just practicing the chain reaction bit here. Okay, we're going to do lots of these kinds of discussions. We look at literature review, spend a bit of time on questions, like 2 or 3 questions on a concept. So, right, so now what is this at pi over 2? The r at pi over 2, it's going to be exactly this sine squared. So, which is pi over 2. Okay, now the sine is 1, the cosine is 0, and then you have pi over 2. Okay, so now, okay, now we have f of this. But what is the r of pi over 2? The r of pi over 2 is the same as 1, 0, pi over 2. Okay, then we've already got this. This f of the 3 components, the x, y, and the z. So x is 1, y is 0, and the z is pi over 2, and therefore now we add y plus z, which is pi over 2. X is 1. Z is pi over 2. Y is 0. X, it's a 1. Okay, let's check this one. Okay, please check this one. Okay, that we did everything above board. Okay, we add first the y and the z, the last 2 components. If we add the last 2 components, 0 and pi over 2, you get pi over 2. And here we have x and z, meaning x and z is the first and the last component, which is 1 plus pi over 2. And here we have the first 2 components, y and x. This one, you get a 1. Okay, good. Okay. So, and now, with r primed, for instance, the r primed is exactly this, but we need to find r primed at pi over 2 also. R primed at pi over 2, which is exactly to the sine of pi over 2 cosine pi over 2, and then 2 cosine pi over 2 minus the sine of pi over 2, 1. Meaning we have r primed of pi over 2. And the r primed of pi over 2 is as follows. Right? Yeah. What do you think that is?
Please check your gradient.
Yes.
Yeah, your gradient with r pi square, isn't it?
Yes. 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 So we
You
will.
wrote
Okay, let's check. Let's see. Okay. Yeah, is comparison because we're dealing with the r primed, which is this one. This is the r primed we got.
No, I'm talking about the gradient.
This
When
one,
you
the
have
gradient.
substituted the r pi, that
Yes.
one, the gradient. Yeah.
Yes. Okay. You're saying there's a 1 here, right? Let's check. What exactly are we supposed to have? So because now the gradient here, first we got the gradient in terms of x, y, and z. And the last component, what is the last component? The last component is y plus x. And y plus x means that we have x, y, and z, excuse, right? So if you have x, y, and z, you'd have 1, 0, and pi over 2, right? And now here we then have y plus x in the last component, meaning y plus x means it's just y and x, which is the first two components. If you add 1 and 0, you get a 1. Right, so if you're adding x and z, so you're adding x and z, right, which is the middle, which is 1 plus pi over 2. Right, so, okay, please check, yeah, what do you think? Because maybe I'm not seeing the mistake. There might be a mistake somewhere. All right, so now if you have like cosine pi over 2 is 0, it's going to give us 0 there. Cosine pi over 2 times everything is going to be 0. Okay, sine pi over 2 is 1, but cosine pi over 2 is 0, making everything 0 here. Cosine pi over 2 makes everything 0, giving us a 1 there, like this. So, as a consequence, what then do we need here exactly? What then do we need here precisely? Well, we then are able to do the usual stuff. What is the usual stuff? The usual stuff is then to say we can be able to get f, which is what is required. The composite function of this one here, primed, pi over 2 radians, which is equal to the gradient, right, which is equal to gradient. The gradient evaluated at f r pi over 2 radians dot r primed at pi over 2. And what is all this here? Okay, the gradient. This gradient, the gradient is equal to these particular things here. These things. We got it to be pi over 2. Okay, I'm not seeing any typo. But remember, I'm just doing this question for the first time ever. I've taken it from the material. Right, so, but the first component for the gradient is pi over 2. Then the next one is 1 plus pi over 2 and 1 dot the r primed 0, 0, 1. Okay, so if you dot this by 0, this by 0, and then it's just going to be 1. So the answer is 1. So any question here, Naledi, or any suggestion, maybe you might be seeing something, you know? You might be
No,
seeing
I am
something.
good.
Good. Okay, yeah, because yeah, I might have overlooked an error, but yeah, I've not been able to quite detect an error. But once again, I'm just doing this for the first time ever in my whole life. But we are following the procedure. But there's always a chance of human error. You know, you can always overlook an error. It's always humanly possible. We are all fallible as humans. Maybe there's a missing number that I've not picked up there. Okay. So, but it's all right. That is the hope. Okay. Now, once again, I want us to discuss tangent planes. Okay, because and we shall discuss level curves as well, because these are the kinds of things you need to understand, and these are the kinds of things that come in the exam. What is a tangent plane? First, we need a formal definition of this. No one is going to ask you in the exam to define a tangent plane. But now, a tangent plane to f at x equals vector p. Right, now, definition 7.5.4. Let f be an Rn to R function and p be an element of the domain of f. If f is differentiable at x equals p, the plane in Rn plus 1 with equation xn plus 1, which is f of p, vector p, plus x minus p dot the gradient. This is called the tangent plane to f at the point p, or at the vector p. Right, so it's something that you need to take note of, as a matter of fact, there. Okay, let us continue to think about this and make sure that we're able to find the tangent plane in the exam, given a situation. Right, so take a look at this definition and move on. All right, there are given remarks that are very important. For instance, if n is 1, so we are dealing with a one-dimensional space, then the gradient of f becomes the ordinary derivative f primed. Okay, one-dimensional space, then you have f primed as the ordinary derivative. So if we write x and y instead of x1 and x2, equation 7.1 becomes this. Right, so in other words, sometimes you can write x and y, because we're able to see that here we have like xn plus 1. You can just call it y. And then wherever there is xn plus 1, you can put, for instance, a y. And then we have wherever there is x, we obviously maintain the x, and this is f primed. So this here, which is the equation of the tangent to f at p. And now remember that in R2, a plane reduces to a line. In R2, a plane reduces to a line. Right, so yeah, so we continue. Just a minute. Right, I want us to look at the tangent planes.
Yes.
And yeah, I want us to look at the tangent planes, but we still have lots of time. Right, because we are here for I mean, we count 2 hours of time, so we still have ample time there. So yeah, we're continuing. We are going on and on. We are going on and on. So now let us see this one here. Let us see this one here. For example, if n is 2, then you're dealing with a two-dimensional space. We continue, please. All right. So now this becomes this. So we continue. All right. I'm just making sure that I'm communicating with this student as well. All right. So obviously we realize that this can also be written like this. In the event that you are dealing with R3, and therefore now you have an extra component. And now in the place of the y, you put z. And now the p is having 2 components. And okay, yeah. So that now here, the x is having two components like x and y, and the p has a and b, and if we subtract them, it's like right. Okay. And then now you dot that with the gradient of these here, which is the equation of a plane in R3. So we know that this becomes the equation of a plane R3, and this becomes the equation of a plane in the R2 case. So we continue. I want us to discuss the fact that now if you have a curve of the equation z equals f and x and y, then the equation of the tangent plane, this is a plane that is like a tangent. A plane is a two-dimensional structure, like a piece of paper. So you have a piece of paper or just paper, A4 sized, whatever, and it is attached to this particular structure. Now you then would have what you call a tangent plane, a plane that is touching the curve at most at one point. If f is differentiable at p, there is a unique tangent plane to the graph of f at p f of p with equation z equals f of p plus x minus p dot the gradient of f of p. What are we showing here? Okay, the point of contact of the tangent plane and the curve is p f of p. Okay. Let us look at some examples. Now, if we have, for instance, let f be an R2 to R function defined by this function, which is x squared plus y squared. Proof from first principles, that is by definition 7.5.2, you'll see that one, that f is differentiable at x and y equals 1 and 1, and find the equation of the tangent to f at x and y equals 1 and 1. So let us look at this. How do we prove from first principles that f is differentiable at this point? How? So we will actually look at these together. Right, so we'll look at these together. So right in the end, then what then we're able to get here is the, so yeah, we're doing the preparation with the chain rule, and then now we're able to just use the chain rule. We note that obviously given in this instance, the function f is actually x squared plus y squared. What is the gradient of the function? Right, the gradient of f, x, and y. Okay, this is the function. So it's always the derivative of the x, which is 2x, the derivative of the y, which is 2y. This means you have the gradient of f1 and 1 at this point. So if you put 1 and 1, then in place of x, you put 1, and in place of y, you put 1, it becomes 2 and 2. Right, so what then are we able to achieve out of this? So we proceed to then say you put the point P with components 1 and 1 and X with components X and Y. Then the local. Right, there's something called the local linearization. The local linearization of F at P is given by T of x. Right, and I need to write a bit clearly here to avoid ambiguity. So it is t of vector x, which is f of p plus xp dot the gradient f of p, like this. Now, what is this? We want to find the equation of the tangent because you need to know this in the exam. Now, the f, so it's going to be f evaluated at 1 and 1, xy, right? So the gradient of so what is f of 1, 1? Right, so f of 1, 1, when you put x and y to be 1, becomes 1 squared plus 1 squared, giving us 2. Then we have here plus, we have xy minus 1, 1. It's like x minus 1, y minus 1, dot the gradient. Okay, now of the 1, 1, it's going to be 2, 2. It's going to be 2, 2. And this one here, it's 2 plus. You dot this, the first with the first. So it's 2x minus 2, 2y minus 2, which is 2x, 2y, and this one is exactly minus 2. Okay, with this, we're able to therefore say the tx is equal to 2x plus 2y minus 2. So the equation right now, from the first principles, something we need to state here. Right, from the first principles, there's something we need because they said prove from first principles. Now, the significance of that is that the limit as x tends to p of fx minus tx divided by the length of the vector x minus p, this is equal to 0. Okay, so you must obviously it will always be 0 there, and that is because it's a proof, so it's true that this will always be 0. And because of that is the case, right? And the fact that this is 0, it allows us to say, therefore, right? It allows us to then say, therefore, f is differentiable. It's differentiable at 1 and 1, and the equation. And the equation of the required tangent plane is, right, so the equation of the tangent plane becomes this one we're writing here is z equals 2x plus 2y minus 2. Okay, this is surely one way to actually compute the equation of the tangent plane. Okay, so you take note of this because it is very important and it's very examinable, and you need to be able to understand these and be able to apply these concepts here. But now, moreover, we have a comment to make. We have a comment to make. Right now, the tangent plane to the surface. So we have the surface here, which is the paraboloid. Right. And this paraboloid Z is x squared plus y squared. At the point of contact, at this point, you have 1 and 1 and 2 and 2. Okay, we have 1 and 1 here because xy is 1 and 1, but at this point, when you put the x,
So
which
how
is 1
do you, sir?
come again?
I'm saying, how do you know it's a paraboloid?
That's a good question. How do we know it's a paraboloid? Well, because it is actually z is x squared plus y squared, and it is from school, we know very well that if z is x squared, or the most popular is y equals x squared, which is ax squared plus bx plus c, and in 2 dimensions, this becomes a parabola. Right, but paraboloid therefore becomes the 3D setup of it. So in other words, we can, if we look at these now, z equals x squared plus y squared becomes a paraboloid because it is a parabola in 3 dimensions. And now, moreover, if we take at the point where x, y is 1 and 1, we can put x and y both 1 and 1, 1 squared plus 1 squared, so that we have 2, z equals 2. Okay, if z equals 2, then we have here a point of contact. Point of contact of the vertical line through the 1, 1, and the actual corresponding z value when x and y are both 1 here, because with x is 1, you have 1 squared and 1 squared, which equals 2. Okay, yeah, equals 2. And therefore, we have the point of contact there. But now the tangent plane to the surface at the point that is that. So here is the plane. It's this one here. So it becomes the tangent plane that is going to touch the paraboloid at most at one point. So it's like a paper that touches this structure that is like a jar. That is like a jar. And now, if this is a jar that can contain water, and now you have paper that you have attached to the side. And this paper you have attached to the side at a point whose coordinates are 1, 1, 2. This paper it's the tangent plane. What is the equation of the tangent plane? It's z equals to x plus 2y minus 2. How do we know that the equation of the tangent plane is z equals to x plus 2y minus 2? Because we found it before. And now we know the equation of tangent plane at this point. And we know very well, therefore, that the tangent plane to the surface, z equals x squared plus y squared at the xy equals 1, 1, has been determined. And that is what we have. And we move on. We move on to the next point. Right, and we highlight, okay, there's a remark we need to make about differentiability versus continuity and the implications that arise out of this. Obviously, this module is not very conceptual in the exam, so you expected that differentiability and continuity are not heavily contested concepts in exams. However, the converse of the theorem 7.5.7 is not true. Differentiability implies continuity. Well, yes, so a differentiable function is always continuous. So if ever it happens that you have a function that is differentiable, please, you know that if it is differentiable, it is automatic that you say it is continuous. So differentiability implies continuity. So now if you have a function that is differentiable, it implies that the function is continuous. It is continuous. But continuity does not imply differentiability. Function that is differentiable is continuous. But now the reverse is false. So in other words, a function that is continuous, it's not necessarily differentiable. For example, the R2 to R function depicted in figure 7.5, this one here, is continuous at AB, right? So you're able to look at this function and say, it is continuous at AB. If this is A and that is B, it is certainly continuous at AB, which is the point there, AB. It is continuous at the point AB. However, since right, but it is not differentiable at AB, since its graph has a sharp corner at that point. So we're able to see that here is the graph, and this graph has a sharp point, and at this sharp point, normally we have what we call a cusp, right? Because we have a cusp, and a cusp is a characteristic of a function that shows that the function has a sharp vertex at the point, right? And hence does not have a unique tangent plane at that point. So at this point does not have a unique tangent plane because there's no way you can be able to claim that you have a unique tangent plane because the point is sharp, and the tangent planes, tangents in mathematics are defined for smooth functions. Then you can have a tangent. What about if you have a graph like this? Then we do not define tangents for this, but we define tangents for smooth functions. That is why these functions must be smooth, right? If
Why can't you find a tangent? The tangent is a point on a graph.
like this one, because like this one can be seen as the graph of this function, you know, right? The absolute value function like this, or the absolute value function this way. These functions here are not differentiable. Why? They're not differentiable, and therefore they're not differentiable. Okay, differentiability can be defined at a point, but they're not differentiable at the vertex. They're not differentiable at the vertex. Why? Because the vertex is too sharp. And now if you look at the slope this side, okay, the slope at this side is going to be 1. The slope, so like the gradient. If the gradient here is 1, and then what is the gradient on the other side? The gradient on the other side is sloping down, it's -1. Because the slope of the tangent is changes so immediately, so instantaneously, then we then say these functions are not differentiable. But also, most importantly, we can see if in the 3D case, if a function is like having a sharp corner, then it's not differentiable at that sharp corner. But now it means, therefore, because it's not differentiable at that sharp corner, there's something you can say. You can't get a tangent, a unique tangent at that point. Okay, and this applies to our absolute value functions. Right, absolute value functions we study at first year. Okay, but now the functions must be smooth for us to speak of differentiability. Okay, this one is an example of a case we're saying, but it's not differentiable at AB since its graph has a sharp corner at that point, and hence does not have a unique tangent plane at that point. So there's no way you can actually attach a unique tangent plane there. Why? Because okay, in first year, the absolute value function becomes one easy example that is used to show that the absolute value is continuous, because continuous means there's no gap, there's no break. Yet now, if you find the derivative here, you'll find the derivative is 1, the derivative here is -1. So this is not a continuous function, and therefore it is a characteristic of a function that does not have a unique tangent plane, and therefore obviously not differentiable. Okay, we're here to spend a bit more time on these, but once again, in this module, it's not a big deal, this section on the contingent differentiability. It depends on the nature of assessment, but over many years of assessment, differentiability and continuity. Okay, you need to learn continuity. Yeah, yes, and you can, this comes in limits. Yeah, in limits, when you discuss limits, then you can determine whether the function is continuous or differentiable at a point. We continue. Let's discuss contours. Tangent planes to contours. Recall that the contours of an R2 to R function are curves in R2. See definition 3.5 in the study guide 1. We say that a vector is perpendicular to a curve. Okay, this is very important. A vector is perpendicular to a curve at a given point if it is perpendicular to the tangent to the curve at that point. Right, so when is a vector perpendicular to a curve? A vector is perpendicular to a curve when it is perpendicular to the tangent to the curve at that point. Our next result gives useful relationship between gradient and contours of an R2 to R function. Let's look at the theorem 7.8.1. Now, suppose f is a differentiable R2 to R function and AB is an element of the domain of f such that f of AB equals C, right? If the contour C of f is a smooth curve, okay, smooth curve. We study smooth curves in calculus in general. Okay, the sharp ones, we know they're not good because they don't have unique tangent planes, and now they're not differentiable at those points and so on, at the sharp points. Right, so now we're saying if the contour C of f is smooth curve, and graph of f and AB is not 0, then the vector gradient of f A and B is perpendicular to C of C at the point AB. Then this vector is perpendicular to C of C at the point AB. If the contour C of f is a smooth curve and the gradient at AB is not 0, the gradient is not 0, then this vector gradient of f at A and B is perpendicular to f at the point A and B. Okay, let us look at the actual implications of these. These ones again is recorded. You don't need to copy all these. You can during your own leisure, watch this video. But I want us to look at a specific example on this. Example 7.8.2. You let f be an R2 to R function defined by this. Okay, let's look at an R2 function. R2 to R. Why R2 to R? We're starting from an ordered pair of coordinates x and y, and we end up with the sum of this, and the sum is for what we need, and it is a number. It is a number. Okay. Then the gradient of f is a two-dimensional vector field given by this. Okay, you can find the gradient of these. The gradient of these, derivative of the x squared is 2x. The derivative of the y squared is 2y. Right, so we continue. We continue. Right, so
Yes.
yeah, the equation of C, okay, what is the equation of C of C? The contour of f at level C is given. Yeah, I want to speak about level curves, and that's the reason why I cited this part. So the level curves become very important in the assignments and other things, and often in the exam, there's not much time to actually, it's not popular to have level curves. But the equation of C, the contour of f at level C is given by this. So the contour of f at level C is given by the function made constant, C, and the constant is called the level. Right, so if A and B is any point on C of C, then A squared plus B squared equals C. Then A squared plus B squared equals C. We know that the vector gradient of FAB is perpendicular to the curve C of C at AB, and its length is the gradient of the length of the gradient of FAB is given by exactly that. So if we agree, therefore, that the gradient is exactly this, then what is the length? If you replace x and y by a and b, so then the length can be seen as the gradient of f, a, and b. And this is exactly the same as the length of 2x, 2y. What is this length? Okay, what exactly is this length here? 2x, 2y. What is this length? 2x squared, 2y squared, which is 4x squared, 4y squared. X squared plus y squared. Okay, which is exactly this. Okay, but yeah, if you're dealing with the f and b, with the a and b, so wherever there is x and y, you can just put ab. You can just put ab there. Wherever there is xy, you can just put ab. Xy, you can put ab. Xy, you can put ab. Okay, if you replace every x for ab, x and y by ab. So you have ab, we have a, b, 2, 2. Okay, because it's 2x to y. Right, and then this is exactly that, and this is exactly b squared, and then the a squared, b squared, and take the square root of 4 is 2a squared plus b squared. 2. Then the square root of this is what? Is the square root of c. Okay. So we know that the vector gradient of f of ab is perpendicular to the curve c at ab, and its length is, okay, we'll find the length of the gradient function. The length of the gradient function is exactly the 2 times the square root of c. Okay, for this function, but doesn't mean it's always the gradient of a function is always 2 times. No, it's for this function. We can visualize the two-dimensional vector field gradient of f by drawing. For a few xy, the vector gradient of x and y with its initial point at x and y. So that this here is x and y. And now we're able to see that the x squared plus y squared is nothing other than what? The x squared plus y squared is equal to something. X squared plus y squared equals c is a circle. All right, so being a circle like this, so now because c changes, then we have too many circles, but the c values sort of increase because these are like numbers for different levels. For f at level c at level c, where c changes, you have too many circles that sort of sprawl upwards, sprawl outwards. We continue. So now suppose f is differentiable in function like that, such that this is the case. If the contour of this is smooth, is a smooth surface, we're starting with smooth surfaces, the gradient is not 0. The gradient A, B, and C, the gradient at A, B, and C is not 0. Then the vector, the gradient is perpendicular to C at that. Right. So in other words, this one, this is very important. So now this one is perpendicular to C at D. Right. And so
sir, can you go back to
okay, yeah.
the previous example?
Yes.
I don't understand why, like, what were we trying to prove here by the 2 square c, like?
Yeah, what we're trying to prove here. Okay, here, remember that we were given this function f of xy, which is x squared plus y squared. And we were looking at the fact that here is the description, figure 7.7, contours and gradient vectors of this particular function f of x and y, f of x and y equals x squared plus y squared. We were trying to then say, in this case, what actually is a contour of f at level c? Right, so we're able to see that the contour of f at level C is x squared plus y squared. So it is just this function equal to the level, which is C here. So we equate the function to C, the constant, and the C, it's the level of the contour. If A and B is any point on CC, then the A squared plus B squared equals C, which is the level of the contour. Now, we went on to then say, we know that the vector gradient, the vector function gradient of AB is perpendicular to the curve at AB. So we are emphasizing, and its length is this. Right. And now, if we're then saying the gradient is perpendicular to the curve at AB, we can visualize the two-dimensional vector field gradient of F by drawing. Right, for a new xy, the vector gradient with its initial point at x and y. Okay, what are we trying to actually be able to say here? We are effectively saying, if we have this particular function x squared plus y squared, and this x squared plus y squared can be equated to C, meaning that we have concentric circles, because when C is a number, then we have a circle, a circle, a circle, a circle, and so on. But now, what is the radius of this circle? What is the radius of this circle? The radius of this circle we're able to see, for instance, because this is like the square root of C squared, and the radius of this circle becomes the square root of C. But most importantly, we're able to see that the length of this particular gradient function is 2 times C, and it is nothing other than, just an observation, it is nothing other than 2 times the radius, and 2 times the radius, it's a diameter. But what we're trying to say here is that this vector gradient of FAB is perpendicular to the curve. What is the curve? The curve of level C, this curve is a circle. So anything that is perpendicular to it, there's a circle, perpendicular to it would be like this. But obviously it is perpendicular. We said that already. It's strange to speak of a perpendicular to a function. We then said that a perpendicular vector is actually perpendicular to a tangent at the point on the curve. So we showed therefore that these perpendicular things here are nothing other than the actual gradients, because the gradients themselves are these. And these vectors themselves are actually vectors that are perpendicular to the curve. What is the curve? The circle, x squared plus y squared equals C. Right. So, but again, we went on to then say we can visualize the two-dimensional vector field, which is the gradient, two-dimensional vector field, by drawing. For a few xy, the vector gradient of f x and y with its initial point at xy. So in other words, you can identify several points and be able to realize that there are vectors that are perpendicular. And what are the vectors that are perpendicular? They are the gradient vectors. The gradient vectors are the ones that are therefore perpendicular to what? They're perpendicular to the curve, which is the circle. Right. Moreover, if a vector exists in this section, we're interested in finding the length of the vector. So if we then say, here's a vector, gradient vector, which is 2x, 2y, what is its length? Its length is this. And therefore, that means that given these particular vectors that are many, we can be able to even determine the length of each of the vectors. which is a vector perpendicular to the what? Perpendicular to the curve. What is the curve? It is the contour of f at level C. Right. We shall spend a bit more ample time on this, I'm sure, in our next meeting, because I realize that it is a bit interesting, but it is potentially very subtle and a little bit confusing. But we need to build more background for this to determine equations of tangents to contours, tangent planes. Okay, there's more on tangent planes that we need to discuss. I'll explain why, because this is very examinable in the exam. So it is normally the case that you will actually be asked in the exam to analyze tangents to contours and tangents to tangent planes to curves and things like that. Okay, I think that it's enough for us to say it's an awesome, it was awesome a little bit discussing on this, having a discussion on this, but we shall, our next meeting, you will let me know. It can be tomorrow. We can look at, or during the weekend, Saturday, Sunday, etc. We'll still have ample time before the exam anyway, but we can look at this in detail. There's more to this. Why? Because it's examinable. There's more to this. But I think that we're gonna call it a good evening now that we have discussed this. But yeah, in our next meeting, we shall go deeper into tangent planes, to curves and contours. Right.
All right. But can I ask, why do you always postpone our classes?
Okay, yeah, apologies. Obviously, I'm sure that will actually from now on be more consistent. Will be more
Yeah,
consistent.
but I want to know why.
It really depends, obviously, if there's a glitch, but I'm sure that if we get started like we are, then we shall be in a position to make the most of our time, And
Okay, do I have to pay for those classes again? Because today it was short and you have, especially this topic of tangent. I don't
yes,
think we have that.
yeah, we've not finished the section on tangents because it is, well, it is a section that is lengthy because there's more to this. I mean, right, we were yet to spend a lot of time on this, but it is lengthy.